All right, let's take a minute or two to go through Progress Quiz 3.3, which is linked via Canvas right above this video if you're joining us on YouTube. So, Progress Quiz 3.3, a ball is launched from the ground at an angle such that its vertical component of velocity is 5 and its horizontal component of velocity is 15. Couple things to keep in mind that some people are kind of mixing up. This is the X, this is the Y. Okay, most of us aren't screwing that up. Vertical and horizontal. Is X horizontal or is it vertical? I heard someone whisper it. This is horizontal and Y is vertical. Keep that in mind. Horizontal and vertical. So when it says the vertical component of velocity is 5 meters per second, the vertical, that's the Y direction. I don't have a picture. I can't believe I didn't draw a picture. I should draw out a picture. But that's going to be the vertical, that's going to be my Y, VIY, and the horizontal component is my VIX. Meters per second, that's velocity, that's velocity, that's velocity. It's a 2D motion problem, 2 lists of variables. It's a projectile motion problem, AX is 0, VIX, VFX is 15. It's a projectile motion problem. Also, we then know AY is negative G, which is equal to negative 9.8 meters per second squared on Earth. Horizontal or an angle launch, it's launched at some angle, therefore it's an angle launch, so we can't put a 0 there. It's not 0, that's really all it says. And then is it a delta Y is equal to 0 problem? Assume it is, unless specifically told otherwise. Today we'll go through one that's not. So that's equal to 0. And some people are forgetting that if it's a delta Y is equal to 0 problem, my initial and final velocity are opposites to one another. So if this is a positive 5, this is a negative 5. From the problem type, my VIX is 15. I'm sorry, from the problem itself, my VIX is 15, my VIY is 5. Now, in order to solve for time, I chose equation number 2. You could use equation number 2. You could use equation number 3. You could choose equation number 5. They would all get you time, assuming this is the list you have. We get a time of 1.02 seconds. And then when we plug it in for part B, how far delta X, equation number 3, is 15.3 meters. Okay, so that's an angled launch, delta Y is equal to 0 problem. Delta Y, angled launch, delta Y is equal to 0 problem. Let me, actually I gotta take a 10 minutes. Switch gears. Now let's pull out your in-class, 2D motion in-class problems. 2D motion in-class problems that we were working through on Friday. 2D motion in-class problems. If you can't find your paper copy and you don't want to use the PDF version that is linked via Canvas, paper copies are right there. So, attendance. And then let's take a look at problem number 7. So problem number 7 on the screen should be the same, and I apologize, I didn't realize my word wrap kind of is this 5 meters per second, and they're on separate lines, so I apologize. A ball is thrown off of a 10-meter cliff at some angle such that the vertical component of velocity is 5 meters per second, and the horizontal component of velocity is 8 meters per second. If the ball hits the ground at the bottom of the cliff, how far horizontally did the ball fall? Angle launch at some angle. Delta Y is equal to 0 unless specifically stated otherwise. This is me specifically stating otherwise. You start at the top of a cliff and it lands at the bottom. That's not equal to 0. They don't start and end at the same height. So let's take a look at this one. We're still going to be working through the problem types of is it 1D, is it 2D? Right? So from I'm going to draw a picture. I think pictures are good. I apologize for not drawing one for that last one. But this is what my picture kind of looks like. The cliff is 10 meters high, so if we say, hey, this is 0, from 0 to here is 10 meters. Keep in mind that delta y is not how high the cliff is, it's how far the ball travels. We need an up and a down associated with that. So when we go, let me get rid of that done. This is what it looks like. A ball is thrown off a 10-meter high cliff. There's my cliff, 10 meters high. At some angle, okay. Vertical component of velocity. Vertical is up and down. That the vertical component of velocity is 5 meters per second. And the horizontal component of velocity is 8 meters per second. If the ball hits the ground at the bottom of the cliff, how far horizontally from here to here does it went? Okay, that's from my problem information. Now let's work through that if-then problem type. Is it 1D or is it 2D? It's 2D. So therefore, two lists of variables. Black marker, time is going to be the same, and that's because it's a 2D motion problem. Black marker, 2D motion, two lists of variables, linked only by time. Remember, when you're plugging numbers in or solving for an equation in the x, you can only use numbers from that column. When you're solving for something in the y, you can only use stuff from that column. Is it a projectile 2D motion problem? Is the object moving freely through the air in both the x and y directions simultaneously? Yes, right? So because of that, ax is equal to 0, which means these two are the same. My vix and my vfx are the same because my acceleration is 0, which means my velocities are constant. And because it's a projectile motion problem, my acceleration in the y direction is equal to negative g, which is negative 9.8 meters per second squared. Projectile motion problem. Green marker, done. Is it angle launch or horizontal launch? Thrown at some angle, therefore angle launch. Is it a delta y is equal to 0 problem? No. I'm specifically telling you it starts on top of a cliff and it lands on the bottom. Delta y does not equal 0. Okay? I don't think technically I can write anything with my blue marker there. It's angled launch. It's not equal to 0 for my VIY. There's no number I can actually have. Red marker from the problem now, we can start filling in some information. Okay, my VIY is equal to 5 meters per second. My VIX is 8 meters per second. VI, I'm going to erase this in a second. My VIY does not equal negative 5. It does not equal negative 5. If I'm going to erase this in a second, if this was equal to 0, then yes, it would be negative 5, but it's not a delta y is equal to 0 problem. So it's not negative 5, we don't know what it is. We do know how far the ball moved in the y direction. It started here, and it went here. The ball went 10 meters. Remember, we need a direction associated with it, and it went down, so negative 10 meters. And we are ultimately solving for delta x. This problem is much like any other problem we've solved before. In order for us to solve for delta x, we're going to have to solve for time in the opposite column first, and then we're going to have to plug that into our original, or into the other column and solve. The thing that happens is our math gets a little messy here. And technically there's three different ways you could solve this problem. I'm going to show you 2 out of the 3. We have enough information in the y column that we can solve for time. So we're going to have to solve for time first. In order to solve for time, you might look at that and say, hey, what information do I have? I have enough information in my y column that I don't know. I don't know final velocity, but I don't care about final velocity. So I'm going to show you 2 different ways. Okay, so you might be like, well, I don't know that and I don't care about that. So because of that, in the y direction, I'm going to use equation number 3. And equation number 3 in the y direction says delta y is equal to VIY times t plus 1/2 AY t squared. So far, so good. We're using Mr. Davies' favorite motion equation, number 3. And why is that? Because he uses it all the time. So we start plugging numbers in. -10 is equal to 5 times t. 5 times t plus 1/2 times -9.8 times t squared. I'm going to do that a little bit different. There. Now, I did that in red to try to help draw your attention to t. Can we solve for t? Sure. But we're going to have to do what? We have both a t and a t squared. So in order to solve for that, we're going to have to use quadratic. Now some of you might be like, yuck, I hate quadratic. I'll show you another one. Some of you be like, whatever, it's just quadratic formula. We do it all the time in math, no big deal. Fine. Some of you can say, hey, I have a TI-83 plus or 84, and I have a program on there that actually solves that for you. Hey, good for you. And I know how to use it. Awesome. Okay? But I'll show you that we can solve for this quadratically. If you say, yuck, quadratic, don't want to do it, I'll show you another way. I surveyed my last class, and it was split 50-50. 50% of the kids said, whatever, I'll just do quadratic, no big deal. The other 50% said, you know what, I'd rather do 2 calculation steps in between, so I don't have to do quadratic. And that's perfectly up to you. Keep in mind, though, in order for us to use the quadratic, it has to be in the ax squared plus bx plus c is equal to 0 format. So we do have to rearrange this. So a little bit of combination. We get -10 is equal to 5t minus 4.9 t squared. Now, we need all this stuff on one side. We could shift both these things to the left, or we can shift this one thing to the right. I'm going to do that. So I'm going to add 10 to both sides. And what we're left with, and then I'm going to rearrange it, I'm going to be left with -4.9 t squared plus 5t plus 10 is equal to 0. Just to kind of remind you, this is your A, this is your B, that's the C. And then, when we set this up, now we always map it, we say x equals, but technically now we're saying t is equal to fix this if I'm wrong, but it's negative b plus or minus the square root of b squared minus 4ac all divided by 2a. I think I got it right. B is 5, so negative b plus or minus the square root of 5 squared minus 4 times negative 4.9 times 10, all divided by 2 times negative 4.9. And then I did this already, and we get t, there's two solutions, right? So it's negative 1.007 and 2.027 seconds. So those are your two solutions to that problem. Now you have to make a choice. But remember, a stopwatch, on your mark, get set, throw that ball off that cliff. You hit 0, you hit start, and your time is 0. So because of that, a negative time is not. What that's really saying is the other half of this parabola would be like over here at time of -1, but that was before the ball was actually thrown, so we can ignore that. Your time is that. That's how you can solve for time if you want to do it quadratically. And somebody would be like, whatever, no big deal. And somebody would be like, eh. So here's the other option. Option 2, and there is an option 3 that I'll mention, but I'm not going to take time to do. The other option here is ultimately we want to get to t. This is still only like part A of the problem. We want to get to t. If we want to avoid quadratic, then we have to avoid using equation number 3. So what we could do is we could solve for this first. We could solve for this then second. And then, so if we use this number, we can solve for time without using equation number 3. And I'll show you that step as well. So this is 2 steps for time. So this is a different way you could do it. So if you're going to solve for this, you would then say, well, I don't really know t. I don't know t. So then we would use equation number 4 in the y direction. VFY squared is equal to VIY squared plus 2AY times delta y. My final velocity in the y direction squared is equal to 5 squared plus 2 times negative 9.8 times negative 10. So my VFY squared is equal to 25, that's 5 squared, plus 196, which is 2 times negative 9.8 times negative 10. My VFY squared is equal to 221.
Which is like
Right.
17. What's the square?
14.
14.
Yes, 14 point something. Okay, so then that's 221. So then we need to take square root. And remember that when we take the square root of any number, it's plus or minus 14.866. Then we have to ask ourselves, right here, when the ball is landing in the y direction, final location, is it moving down, negative 14, or is it moving up at positive 14? And hopefully you realize that's moving down. So then we can go and say, well, this is negative 14.866. Now we can solve for time. And we can avoid using equation number 3. You could use number 5, you could use number 2. I like number 2. VFY is equal to VIY plus AY times T. And now because we determined what final velocity in the y direction was negative 14.866, we can plug in the rest of my numbers. That's equal to 5 plus a negative 9.8 times t. We're going to have to subtract 5, we're left with negative 19.866, which is equal to negative 9.8 times t. By both sides by t, and we're left with 2. T is equal to 2.027 seconds. Now realize this isn't the answer yet. This is really just the time. And I know, we're like, well, yeah, I know. But notice how we solved it quadratically. We got time. We solved it doing 2 steps. We got time. There is a third option, and on the homework it references it, and I'll come back to that on the homework. Quick survey: 1 finger quadratic, 2 finger, 2 steps. How many of you think you would solve this problem quadratically? Just like whatever, it's quadratic, we can do quadratic. 1 finger for quadratic, or I'd rather just do 2 calculations to come up with time. So 1 quadratic, 2 for 2 steps. Bait and bow, quadratic, or 2 step?
2-step.
All right, about 50%. About 50%. 4 to 5. Okay, so it's pretty split, just like my last class was. Okay, it's up to you. It's up to you. It's up to you. It's up to you. Either way, you're going to come up with time. So realize we now know our time. So I'm erasing part of it. That wasn't the answer of the question. That was just a step we had to take in order to get there. The final step is to solve for delta x. And that's equation number 3. In the x direction, because that's 0, equation number 3. Delta x is equal to VIX times t plus 1/2 AX times t squared. Because AX is 0, that whole term cancels out, and we're left with delta x is equal to 8 times 2.027. Our final answer, delta x is equal to 16.216, which rounds to 22 meters. So that's how we can do this. It's up to you, it's up to you, it's up to you. It's either an extra algebra step or an extra calculation, 1D motion calculation using Cat 5, or you solve it quadratically. And I'll give you the tip. If this is not equal to 0 and you're forced to solve for time, and you don't know final velocity, it would be this situation. Let's take a quick look at your homework sheet that you picked up on Friday or Thursday, depending if you're an A day or B day, called Angle Launch Projectile Motion Problems. It's on that front corner of the desk that you grabbed like on the way out. Or it's linked electronically in today's agenda. Problem number 1 and problem number 2 on this worksheet. An arrow is shot at some angles such at 30 degrees above the ground. And then number 2, an arrow is shot at some angle above the ground, and it tells you 60 degrees. The only reason I'm telling you 30 degrees and 60 degrees is they're complementary angles. And one of the things from the here. Worksheets right there.
No, I'm getting.
Oh, okay. The only thing, the reason why I'm telling you 30 degrees and 60 degrees is they're complementary angles. And from that simulation, remember complementary angles land at the same location. That's why, and this is just mathematically showing that. So if you look at answer B and letter B, if you didn't round anything, they're the exact same, and that's the intent of that. You never actually have to use the angles that are given in any of these problems. Yeah, so that's 1, 2, 3, and 4 are delta y is equal to 0 problems. I said, hey, do number 2, the first 3, you have a pretty good understanding then of how, if you know how to do angled launch or not. Let's take a look at the backside real quick. Number 5, Luke Duke from the Dukes of Hazzard drives generally off a 45-degree ramp that is 4 meters off the ground, and it gives you the x direction, velocity, and his y. If Luke lands on the ground, starts 4 meters up, lands on the ground, hey, I'm very specifically telling you it's not a delta y is equal to 0 problem. Number 6 is the problem that I kind of wanted to draw. There was a third way I said you could solve for time. There are parts A, B, C, and D for problem number 6. Circle letter A. Circle letter A. 6A, that's the question I want you to answer. And it says that afterwards, but it says a ball bounces off the floor such that it's going vertically and horizontally. If it goes to max height, then comes back down, and it's caught 2 meters off the floor. Bounces off the floor, catch it 2 meters off the floor, delta y does not equal 0. Part A is the only question I really care about. Question A is how far did the ball go horizontally? Delta x equals question mark. Solve for that. If you can do it like what we just did here, you're done. The problem is over. Okay, and that's what it says. If you get this directly, skip the rest. However, if you get stuck with solving this part, go through parts B and D. I don't know. This is the third way to do it. I kind of quit teaching it this way because I realize most people are either confident enough with quadratic or they're okay with doing it the 2 parts. There is a third way though. And the third way is I tried to outline it in parts B, C, and D. If you want, you could. I'm not going to spend the time to teach it, but you could. You could say, well, from here to here, that's a 1D max height problem. The ball goes to maximum height. And then what you could do is you could say, well, hey, this is max height. This is from our problem like that we just went through. You could. You could say, well, I could solve, and I'm just going to call that T1. I could solve for how long it takes to go from the top of the cliff to maximum height given the components that we have. Because we know at max height, this velocity is 0. It's a 1D motion max height problem. And then we could say, well, from maximum height, I'm going to let that thing come back down and hit the ground. So I can go from max height to the ground, and I can treat it as a 1D motion problem, and I can determine what T2 is. And that's what part B is, and that's what part C is. And then once we have part A and part B, or I'm sorry, B and D, B and C, part B, question, part C, we can add the 2 together to get the total time in the air, which is what D is really saying. What all D is it would be doing like this directly. That's the time you should get if you do one of the 2 methods I taught you today. It's a different option. It's okay. I think we're strong enough with math that we don't have to do 2 1D motion problems, smash them together at a time and do it. So if I were you, I would kind of skip B, ignore B, C, and D. Realize that the answer to D is the time you should get when you either solve it quadratically or the 2 parts. So there's 2 additional angle launch problems that delta y do not equal 0. Your test, like I had mentioned on Thursday and Friday, is going to be on Monday or Tuesday, or Monday and Tuesday before Thanksgiving. If you know you're going to be gone, we should try to make some arrangements. In class on Wednesday, we will spend some time doing some review of angle launch, kind of do some progress quiz stuff of horizontal launch, angle launch, delta y is equal to 0, delta y is not equal to 0. I am looking through the Socrative right now, which should give you a pretty good kind of survey of how you're doing with the concept portion of the test. And a lot of that concept portion of the test is identifying problem types. Is it a 1D or 2D motion problem? If it is a 2D, is it a projectile? If it is a projectile, is it horizontal or is it angled? And then using that kind of problem type sheet, the yellow problem type, because it's a 2D motion, what can you do? Because it's a projectile, well, that means it must be 2D. 2D projectile, what do you know? It's kind of like that check mark of like, oh, because I know this, I can fill in that. And that's what that is kind of designed for. And I'll have that up and running as kind of a review, so you can be looking at that Thursday and Monday going into the test. So if you have questions, please let me know. But that's kind of the plan moving forward here.